get a bunch of locations for crabs in their mini submarines. So one crab's at position 16, another crab's at position 1, and well, on so forth, right? And then you need to put them all in the same horizontal position so they can make this humongous blast to make a hole into some cave system for your submarine to dive into or something. But the trick is you need to get all these submarines, crabs on the same horizontal position. Being the way crabs move, they can only move horizontally. So um, you need to figure out the spot where you have to move all the crabs to consume the least amount of fuel. And the amount of fuel is 1 fuel per horizontal delta. So I started solving this, and not wanting to fall into the trap of yesterday, I thought it would be better to keep track of crabs at a position instead of the position of all crabs, fearing that maybe, I don't know, part 2 would make crabs grow or, multiply or whatever. Or part 2 being a very large file, which the actual input is kind of large. So I did solve part 1, that we can see probably when I go to our little API Swagger endpoint. Go to part 1. Maybe we first run it with our example input, these couple of crabs at these positions. So again, you won't see me selecting the file for some odd reason, but I'm opening the example input, which is basically this example line. And then when we run it, I made an extra thing into the output of the API to tell us how long the solution, excuse me, how long the solution ran for. And the solution is 37. So the least amount of fuel to put all the crabs in the same position is 37, which is the solution from the example. So when we look at the code, we're going to parse all these crab positions. I'm going to keep track of crab at a little stem that takes keeps track of all the crabs at a certain position. Of course, we need to keep track of the width of all the crabs. So I'm starting out with a maximum x position of -1, parsing the file, sticking the amount of crabs at that position to the right value, and keeping track of our maximum position. Then, this warning comment is already working. Then I need to brute force all the all the fuel costs for moving all the crabs to one position. So I'm gonna loop through all positions, and then I'm gonna see if I'm gonna move a crab from, so the first loop we're gonna see move all crabs to position 1, then take all crabs, all positions, and then calculate the fuel. And then if the fuel is lower than the lowest cost, which I thought I start out that this would be quite low enough. If it's lower, then that's going to be our newest lower value, and then that cycles round, doing a brute force attack on all these crab movements, finding the one with the lowest cost, and it finds us the solution 37 in, where's our thing, 1 second. Right? Sometimes I think it even runs in 0 seconds. Yeah, this one runs in 0 seconds. That's cool. So it's a rough time that we just measure by the REXX function time in seconds. So we're just subtracting these two time values, and then we have a rough estimate on how long it ran for. But when we run this with our real input, we hit the brick wall already because it's running, and you can see it's running, and it's running and running and running and running some more, which is annoying because it shows that this comment over here why am I brute forcing this? It was a right comment when I started doing it, and we're done. Right, takes us 21 seconds to reach our answer, which of course you can see here was the correct answer, 345,035, which is this one. Maybe it's a bit small. Get that a bit bigger. Maybe that's nicer. Right. So before we go on to part two, which I've already solved the brute force just by keeping it running and then checking back later, I want to make this code for even part one run a bit faster than 21 seconds. So thinking about this logically and thinking back to, I think it was, I don't know, some DB2 session where someone said the best SQL is the SQL you don't do. I'm going to plot that to this REXX. So the best REXX we do is the REXX we don't do. So thinking about that, if we loop through all these position of all these crabs, right? So there's not a real nice picture in this example, but I'm envisioning this with like position 0 has 1 crab, and position 1 has 2 crabs, and position 2 has 2 crabs, and 3 has 0 crabs, and this whole list of crabs at a position. If there are, let's see, if there are no crabs at a certain position, it isn't really smart to move them all there, because you're not going to keep a crab at its original position. So that's just a stupid thing to do, in my opinion. Also in the code, I'm seeing here that I'm calculating, what is this? I'm calculating the distance between those two things, and I'm recalculating that all the time, that's okay. And all right, so I think over here, when we have no crabs at that position, it might not be smart to move them there, I think. So we're gonna see if that works. And so we're gonna say if crabs at position I, right, which is that thing that we're filling up here based on our input. If there's no crabs there, we really don't want to move all the crabs to an empty spot, because that doesn't feel right. So then we just iterate, which means, don't do all of this in the loop, just, get to the next one. Yeah, let's run that. So 21 seconds for this answer. I'll remember this thing. We'll run it again. See what we get. See what we get. Still running for a long time.
5 hours later.
Did we even save this? I don't think we saved this. Uploaded successfully. If crabs at dot. Oh, there's no S there, right? So this is useless. I was going to say, why didn't it change anything? It had to at least skip some data. So we execute again. Now, oh, right now we're running in 7 seconds. So that's a threefold improvement. Let's just see if that was a lucky streak, or we got some extra cycles on our ZOS system, or if it was really indicative of a better solution. So yes, that's good. That already improves it by a lot. Then over here we're looping through all the crabs again, calculating the distance that crab needs to travel to go to that position I from the loop, multiply it by the amount of crabs on that position, and add that to the fuel cost. So over here again, if we're checking a position that doesn't have crabs on it, it's a bit silly to calculate the distance between that position we want to move it to and the position where there's no crabs, to then multiply that by 0, and yeah, that's silly. So we do the same thing. If crab, not crabs, crab at dot j equals 0, then iterate. Yeah, save and run. So let's see if we can improve that 7 seconds even more. I think it will improve something. 1 second. Well, that's 1/7 of an improvement, which is still better than nothing, to be honest. So maybe that's as good as it gets. Can we get rid of more weirdness? Make it more efficient? I'm not sure. If there's no crabs, can we like skip the entire loop? I don't think so, because we need to check the next one. No, I think this is just it, basically. Yeah, so then we copy that to day 2, which already had the copy of our bad code. But for part 2, which I've solved the bad way, I don't know how long it ran for, but it ran for a long time. We do the same thing, only our fuel calculation is different. It's gonna be like moving 1 position costs 1, moving 2 positions costs 2 for the second step, and the third step costs 3. So it's basically this Gaussian thing, 1 plus 2 plus 3 plus 4 plus 5 plus, this stupid thing. This stupid thing, so we need to use that Gaussian formula. What is it? That thing that says something times something plus 1 divided by 2, right? That Gauss, what is it? Gauss sum of integers. Yeah, that trick, right? Gauss summation, and that is this. Go away, you and your pop-ups. No, back again. Well, we do this sum, and then it ends up to this coolish formula. So for part 2, our fuel cost is not just the distance times the amount of crabs that move that distance, but maybe we take our distance. We take our distance equals that, and then that Gauss sum equals, right, it's our distance times our distance plus 1 divided by 2. Of course, still times the amount of crabs that need to move from that spot. I think that's it. That should solve it the better way than I did it earlier. So let's go to part 2 and try it out. So curious if I'm recreating the same result with totally different code. Execute. Maybe we should have done it with the example first. Maybe this runs for ages. Maybe it doesn't run for 8 seconds. That's good. And I think, yeah, that's our correct answer. So that's the cool thing. Don't do what you don't need to do is, I think, the major lesson for day 7. And maybe relearning the Gaussian sum trick thing, which is just so much better than doing this in some weird loop that I've done earlier, where you just brute force that thing, which is not the smart way. So that's cool. That's awesome. And can't wait for day 8.